Hi, this is Mrs. Basin, and today we're going to talk about reaction mechanisms. So we've been talking about how we can change the speed of a reaction, why reactions occur, collision theory, those types of things. So now we're going to look at the actual steps that a reaction could potentially go through to get to the overall equation for the reaction. So reactions can occur in one single step. That is possible. Like we said, if something is unimolecular or bimolecular, it's more likely to occur in a single step. Termolecular, it's very unlikely that those would occur in a single step, which requires them to usually be broken up into multi-step reactions. Each of these processes that add up to the overall reaction are called elementary reactions or elementary processes or elementary steps. So when we're thinking about these things, if we have what's called a multi-step mechanism, that means we have more than one equation that adds up to the overall equation that we would write, more than one step for the reaction to take place. One of those steps is going to be slower than all the others. So let's imagine if we are going from Highland to the Galleria. If we break that up into 3 steps, the first step would be to get from Highland to the bridge, to Poplar Street Bridge. The second step would be to get across the bridge, and then the third step would be to get from the other side of the bridge to the Galleria. So those are our 3 steps. Usually the rate limiting step in this scenario here is going to be the bridge. So it doesn't matter how fast you can get to the bridge. If there's a traffic jam on the bridge, that's going to slow down your overall time. Same deal if you get across the bridge and you can get from the bridge to the Galleria quickly. If there was a traffic jam and you sat on the bridge for a long time, that slows down the overall process. So that's called our rate determining step. That's our slowest step. If you're looking at a reaction diagram for this or a potential energy diagram for this, this is the step that has the highest activation energy. So when we look at this, the rate determining step, like we said, is the slowest step. So if you look at this diagram here, you can see the uncatalyzed reaction. And what we talked about was a lot of times when you have a catalyst, it gives it an alternate pathway. So instead of this having to happen in one step, it gives it the option to happen in 2 steps. So each of the intermediate steps, because these are 2 separate equations, has its own activation energy. So in this case, the slowest step is going to be the second step, because the second step has higher activation energy than this first step. So this step here, the second step of the reaction, we would call it the rate determining step. The other thing that you can see when you have a multi-step process is something called, you can actually see the catalyst, and you can also see things called intermediates. So a catalyst is something that's present at the beginning of the reaction, and then it shows up again at the end, unchanged. So it takes part in the reaction, but it's not included in the overall reaction because it's not a reactant or a product after the reaction has taken place. An intermediate is something that's made in one step and then used up in a subsequent step. So it's, again, does not show up in the overall reaction because it's made and then it gets used up in the next. It would be a product in step 1 and it would be a reactant in step 2 and it would get used up. So here's a proposed mechanism for the decomposition of hydrogen peroxide. So you can see instead of it happening in one step, it's broken down into 2 steps, and you can see there's a couple extra things going on there. The overall reaction is the hydrogen peroxide decomposing into water and oxygen, which is what we know is the equation for the decomposition of hydrogen peroxide. So what you can see here is you can see what a catalyst looks like. So the catalyst is present at the beginning of the reaction, but then it shows up again at the end. And notice if you add these 2 equations together, that's what gives us our overall equation. It's a reactant here and a product here, so the I minus cancels out. It doesn't show up in this final equation down here. For step 2, or I'm sorry, back to step 1, step 1 produces this IO minus, and then in step 2, the IO minus gets used up. So again, it's made here, used up here. It's on opposite sides of the equation, so it cancels out. So it also does not show up in the overall equation. So the first thing you want to make sure you can do is tell the difference between a catalyst and an intermediate. So a catalyst, again, is going to be present at the beginning and then show up again at the end. The intermediate is going to be made in one step and then used up in another. But neither one of those show up in the overall equation because they both cancel out. So let's look at an example problem here. So here's the proposed mechanism for a reaction. So you've got your 2 steps, and then we don't know what the overall equation is because that's one of the things we're going to find out. So what we want to look at is we want to figure out what is the catalyst, what are the intermediates, and then what is the overall equation for the reaction. So when we're looking for the catalyst, we're looking for something that shows up in the beginning and then comes back at the end in one of the final steps. So chlorine shows up here and then comes back here, but it's going to cancel out because there's only one of them. Okay, so our catalyst would be Cl. For our intermediate, we're looking for something that's made in one step and then used up in another step. So if you can see here, you can see ClO is made here and then it's used up down here. So that's our intermediate. And then finally, to get the overall equation, and sometimes it's easier to do the overall equation first before you start looking for your catalyst and your intermediate, but we're going to save it till the end for this one. So what you do here is you're going to add these two equations together. Anything on the same side, all the reactants get added up, all the products get added up. Anything that's the same you can add together. So like these O3s you could add together, these O2s you could add together. If you've got something on one side and something on the other side, they cancel out. So the Cl's are going to cancel out and my ClOs are going to cancel out. So my overall equation here is going to be 2O3 yields 3O2 because I've got 2 here and 1 here.